Okay, so we learned about magnetic fields and how to represent them in 3 dimensions. We saw that particles don't feel a force when the particles are at rest. We saw that the faster they move, the greater the force. We learned how to figure out the direction of the force. And then we learned that we could use these magnetic fields and this idea of changing force direction to trap antimatter or regular matter in a vacuum chamber using a magnetic field. And we worked through all of that and we learned how that process worked using some simple formulas. And then today I'd like to talk to you about the second use of our magnetic field, and we're going to use it in combination with an electric field to produce what's called a velocity selector. So the first time we ever did something like this was a scientist in the late 1800s whose name was J.J. Thomson. At the time, he did not even know, in fact, nobody knew, that electrons were actual particles. He used this equipment to actually figure out the ratio of the electron's mass to its charge. He helped to show that the electron was a unique individual particle, a unique individual bit of matter. We're not going to quite use it the same way now because we know the electron is a little charged object. Instead, we're going to use it to select velocities. So what I mean by that is we may have a contraption that is shooting electrons or alpha particles or any other type of charged particle, and it might have a hodgepodge of different speeds. There might be all kinds of different speeds present in our beam, and we want to select out the speeds that we do not want, speeds that are too fast, speeds that are too slow. It turns out we don't need a little gremlin inside our machine to do this. We can do it with some basic physics. Okay, so the way this works out is you can see we're firing negative particles. They are entering into our area, and the electric field is deflecting them upward. And it's deflecting them so much that they're colliding with the positive plate. This should not be surprising that a negative particle is attracted to a positive plate. The magic comes in when we combine the electric field from the capacitor with a magnetic field that we generate external to our device. So we might have a north pole here and a south pole on the other side. And if it's an electromagnet, we could change the strength of those poles and we could change the strength of the field. And watch this again. Now we have a magnetic force that is acting downward. We could get that from our left-hand rule. Negative particle, left hand, field going toward Miss Dare's room, there's a force going down. So the electric field is trying to get the particle to go up. The magnetic field is trying to get the particle to go down. And if we tune it just right, those two forces will cancel out and our particle will go perfectly straight. The magic of this is that only one velocity will make it through this velocity selector. The ones that are moving too slow will hit the top plate. Since the magnetic force depends on speed, as they get faster, the magnetic field will get stronger and stronger. So the ones that are moving too fast will collide into the bottom plate. So what we do is the only velocity that makes it through will be when the force electric is exactly equal to the force magnetic. So we took a bunch of speeds for a bunch of particles that we cannot even see, and we guaranteed ourselves that anything that was moving at the wrong speed does not escape from our system. Only the particles that have the proper speed would stay in a straight line. This is going to be an important first component in much more complicated high-tech devices. It helps us get the velocity that we need. Okay, so again, it would look something like this. We would have an accelerator here, and although we learned before how to calculate velocity leaving the accelerator, we cannot guarantee that our particles are actually going to be at that speed. We assume that the particles started at rest. That may not be true. We assume that the particles started right at that plate. May not actually happen that way. So we may want to add another component, and that is our velocity selector, that will make sure if it's going too slow, it'll be selected out. If it's going too fast, it will be selected out. And only the one moving at the speed that we want will pass through. So how do we figure out what that speed is going to be? It's actually quite easy. You find the electric field inside the deflecting capacitor using our voltage equals E delta X. Again, delta X is the distance between the plates. You then find your force electric. You need to know the charge of your particle. If it's an electron, that's easy. It's charge of an electron. If it's like an alpha particle, it's twice the charge of the electron. Once you have the force electric, you set that equal to force magnetic, and only one velocity will be true when electric equals magnetic. So you solve for this velocity, and that'll be the velocity of the particle leaving the selector. So that is our second use of the magnetic field, to select out the unwanted velocities and only allow one velocity to make it through. All right, and it would look something like that. You would need to know how much voltage there is on the deflecting plate, and you would need to know the strength of the magnetic field. Two things that we can get. From that, we can figure out velocity.